So, okay, we're back to the second section today. We have Michael Murray, who's going to tell us about an introduction to benign overfitting in neural networks.
All right. Thanks very much. And yeah, big thanks to the organisers. Such an awesome venue to get a chance to get talking. So yes, thank you very much. So yeah, I'm going to talk about, as Angelique was saying, benign overfitting. And in particular, I'm going to try and give an introduction to the topic, maybe in the first half, and then later on try and move on to consider how we characterise it in neural networks. So that's kind of a rough outline. More specifically, we're going to discuss these kind of four things. Probably spend most of our time on the first two because I'm probably assuming most of you haven't looked at benign overfitting much before. But maybe we'll see how we go. We'll go on to 3 and 4 as well. Alright, so first of all, let's maybe think about what exactly is benign, tempered, and catastrophic overfitting. So hopefully if you've done any form of machine learning, you're familiar with the notion of what overfitting is. I think the following example is, for me at least, kind of very nice, simple, intuitive illustration of this. So let's suppose I'm trying to learn the identity function, which we've got on board here. And to do that, I sample some points. Of course, I don't know it's the identity function in advance. And so I just have access to these kind of black crosses, and these are the points I've sampled. And now I want to fit a polynomial to this data. Okay? And so if we fit a low degree polynomial, so d equals 5, this is not Rishi's polynomial basis, I guess, this is just monomials. Now with d equals 5, we're getting something quite nice and smooth that quite accurately approximates, so no surprises there. But it probably doesn't surprise you, as we get d larger, we get to the point where we're interpolating our training data perfectly, right? So you can see this red line, which corresponds to d equals 20, goes through every one of my little crosses very, very well. The issue is, it's completely useless when it comes to actually generalizing on data outside of the training set. So this is, I think, a classic example of overfitting. The kind of takeaway from this illustration or example is that without explicit regularization, expressive models can catastrophically overfit noisy data. So that's something we should always be aware of, be mindful of when we're training models. Okay. However, it's not maybe quite that simple. So, it's not necessarily the case that data always leads to this, right? So let's look at another example where we're trying to learn a classifier. So I've got some f star which maps from vectors in RD to minus and plus 1. I'm going to consider a linearly separable problem, so I'm going to consider a substituted partition of the interval minus 1 and 1. The right-hand side is going to be plus 1 points, the left-hand side is going to be minus 1 points. And then I'm going to use a training sample of this, as I've said, so these blue and red dots. I'm then going to choose some parameters of my network. In this case, I'm going to train a very small, simple NLP. I'm going to try and fit this problem and see how I do. And if we do this, then for width 10 networks, we see, and here the width is basically a proxy for complexity, just like the degree of the polynomial is. As I increase the width, you'll see that I don't see any form of overfitting. I'm kind of, well, I'm finding the correct point because there isn't any noise in this problem, right? So even though my model in some sense is getting more and more expressive and powerful, it's still choosing the kind of simplest problem, or simplest solution. Now we consider a corrupted problem. So in this case, we have some clean problem, but then we corrupt some of these points, so we can kind of switch around some of these dots. So this dot was blue and now it's red. This dot was red and now it's blue. And this might, for example, this could be problems in the way you're sampling your data, or it might basically reflect the fact that there's some features of the data that you're not party to, right? So there might be a third feature, maybe going into the wall. We don't have access to this, but depending on that, you might get a flip of the plus or minus 1. So there's a number of ways you can think about why these corruptions might take place or come into the problem. And now I want to try and fit my my neural network to this kind of corrupted problem. And I want to see how much do these corruptions, there's a few of them, how much do they impact the performance of my model? Okay. So we can see with a shallow network, so one that's maybe not too complex, like I guess a reasonably refined function class, we don't see too much compromisation of performance, but as I increase the width, it gets worse and worse, right? But it's not, I'd say, compared with the regression example, it's not completely terrible, right? So it's not great, but roughly speaking, most of the mass of the kind of red part of our classifier is on the right, and blue is still on the left. Okay. So from this, I would say the following. So without explicit regularization, expressive models can overfit, but it isn't necessarily catastrophic. Okay? So this kind of leads us to this maybe kind of perspective where overfitting is maybe a little bit more nuanced than classically we might have thought. So we can identify the following three categories of overfitting resulting from this perfect interpolation of noisy data. So one is the catastrophic case we saw right at the beginning. So this is when a small amount of noise implies a very significant excess risk. The third, or second, is tempered, where the excess risk grows in some sense with the amount of noise in our system. So maybe a little bit of noise compromises performance a little bit, but a lot of noise still compromises a lot. And then the third is benign, in which below perhaps some noise threshold, so we can think about this in the classification example, basically as the number of corruptions, we see marginal excess risk. In some sense, it's still optimal in some sense, despite this problem. Okay? So I guess the point I'm trying to say here is that our theoretical understanding of all three of these things is pretty limited. So in the past, mostly we just think of kind of overfitting, but my point here is maybe that overfitting isn't always bad, but it can be, or it can kind of be okay in the middle. And we should try and have some mathematical characterization of why that is. And so, yeah, I'm going to focus mostly today on benign overfitting, just because in many ways it's the easiest one, and I'm kind of trying to give you some intuition into what that is. All right, so connecting back maybe with some of Guido's talks on things like uniform convergence and some of the stochastical statistical learning theory, I want to highlight that benign overfitting cannot be explained by recourse to uniform convergence style arguments. Okay? So to see this, we can do the following. So I'll just add some notation. So let's suppose we have some distribution on some spaces x and y. So y we can think of as our targets or labels, x we can think of as our features, and we've got some unnamed distribution p. Then we consider some training sample. So that's endpoints, xi, yi, so these pairs. We'll assume they're drawn mutually ID for convenience. And then we've got some non-negative loss, L, which takes in 2 points in y and computes some measure of like similarity, maybe we think of that for now. And then we're going to say that for any measurable function g from x to y, we're going to find population risk is just the expectation with respect to p of L gxy. And then the empirical loss, empirical risk, again as well, kind of similar to what I guess Rishi was showing in the last talk as well. So nothing really too surprising there. What's nice about this though is it allows us to consider the setting where our function, we're not necessarily saying there is some perfect target function, right? It allows us to consider these noisy settings. So I'm also going to say let f star be the argmin, and I'm considering f over the just measurable function, so very, very general, of LF. So this is going to be the Bayes optimal model. And then I'm also going to define the empirical risk minimizer f hat, and that's just the argmin over f, probably in some function class, but we're not too worried about being specific about that now, with respect to the empirical risk. Okay. So then the kind of assumptions we need to consider the benign overfitting setting. First of all, if the problem is noisy, meaning LF star is greater than 0, this means that, of course, there is no kind of perfect target function. Right? There's this noise in our problem, which is going to lead us to cause some difficulties. Right? The second one is we are considering the setting where we're still interpolating this noisy data. So we've got L hat f hat equals 0. And then the third one is that we're going to assume, just for simplicity of the argument I'm going to present, that the losses on each point of my sample are sub-Gaussian. This isn't really necessary, it just allows us to invoke a very straightforward concentration of that. So to this end, let's consider the excess risk, right? So this is the population risk of our empirical risk minimizer, the difference between that and the population risk of the Bayes optimal model. And so we can do the following very simple and very standard decomposition. I'm just going to add and subtract L hat F hat, and I'm going to add and subtract L hat F star, and I'm going to rearrange it so that we identify the following kind of three groups. So we've got this one here, which in some sense is the difference between the ERM population and empirical risk. This one, which is the difference between the empirical risk of the ERM and the empirical risk of the Bayes optimal. And then, of course, the final one is the empirical risk, the difference between the empirical risk of the Bayes optimal with the population risk of the Bayes optimal. Okay. And so, how do we essentially want an upper bound on this quantity, right? This excess risk. So, how do we kind of deal with each of these terms? Well, this one on the right-hand side f star's fixed, right? So it doesn't depend on the sample we're drawing at all. We're going to be able to use some kind of law of large numbers style argument. In particular, that's why we've seen the sub-Gaussian stuff that we did on the previous slide, to show that this concentrates as n gets big, the number of samples gets big. This one, of course, is non-positive, and it's non-positive for a very obvious reason that f hat is the minimizer, or the the minimizer of L hat. So this can only ever be as big as large as this. This is always going to be, sorry, it's only ever going to be as small as this. So this will be non-positive. So we can kind of ignore it for now, because we're trying to do an upper bound. And then classically, this f hat minus L hat, f hat, this would be something we would try and control using some sort of Rho math complexity style argument. Okay? But for that argument to hold, we're going to need the expectation of this quantity, these two quantities, to, in some sense, converge to one another, right? And that's not the case when we're talking about binomial fitting. So this is what we just said. We can say this right-hand term is roughly O n or 1 over n square root n. This is less than 0. But the problem is, we're assuming if we're in this binomial fitting setting that we're interpolating our training set. So this thing just vanishes, or it's 0, right? So we're left then with just this upper bound, and this thing is always positive. This is just some positive constant, right? So it doesn't matter how big we make n, we're never going to be able to ensure this bound in some sense converges towards 0. Right? Hopefully that's clear. Nothing very clever going on. We're just trying to say that uniform convergence style arguments don't really help when we're trying to work with the binomial fitting setting. All right, so now let's talk about, okay, so what's the summary of that, right? The problem with maybe these statistical, like classical statistical learning theory methods and approaches is that they don't really consider the algorithm, right? The fact that we are trying to do some form of empirical risk minimization. Right? We just typically take the supremum over the functions in our class, and we try and bound that instead of working with the empirical risk minimizer itself, right? So for that reason, we need to maybe take a slightly more refined analysis and actually try and understand what's going on in the optimization procedure directly. So to frame this problem, I'm going to have to make some kind of progress in the kind of analysis of this problem. I'm going to have to make some pretty significant assumptions on the data. So this is the problem setup. I'm going to imagine my features xi consist of 2 components, a signal component which looks like this, right? So just a rank 1 subspace v plus or minus v. And the idea is that there is the clean label, which is in some sense the correlation of x with v. And then we're going to have this other component, which is going to be the input noise component. And we're going to assume that's, just for simplicity right now, orthogonal to the input signal component. And then the idea is that this thing is going to be in some sense isotropic, and we're going to be in some high dimension D. And so these things are going to be kind of roughly orthogonal to one another as well. And so we can think of it as follows. The V encodes what the input's label, or the clean label, but the NI is going to be in some sense a unique signature for each input as well. So for clean points we're going to fit by learning the V component, and the corrupt points we're going to in some sense override this V component and just learn their unique signatures. That's the kind of rough intuition behind how we can maybe prove kind of an IO. Okay. So then I'm going to make the following assumptions on my labels. So there's this beta I, which is our kind of poisoning function in some sense. It's going to corrupt certain indices I and split them from being -1 to 1 and vice versa. For simplicity, I'm assuming I've got a balanced training sample. So I've got equal numbers of +1 and -1 points. And then my xi is going to look like something like this, right? So I've got the true label multiplied by some v component, and then I've also got this term gamma here, okay? So I've got square root gamma, and then square root 1 minus gamma multiplied on the other side. This beta I and I, we're assuming symmetry, so this is just for convenience, right? It doesn't actually change the distribution. So beta I and ni are equal distributions, just for convenience. So you can kind of ignore that. But the key thing I want to kind of point out then is this kind of gamma term. This, in some sense, is trading off the signal versus the noise component, right? So if gamma is very, very large, then we're saying our inputs have a lot of signal. Most of the norm of our input is going to be signal. Whereas if gamma is very small, then most of it's noise. Okay? So the point we're going to look at is basically saying, okay, as I vary gamma, how does my model change, or how does the behavior of my model change? So you can visualize this maybe as follows. We're going to have 2 disks of data. One of them is going to correspond to the kind of negative one label, one's the positive one label, and then we've got points. Our noise is uniform on the sphere, so you can imagine that kind of as disks, and then the gap between them is just going to be 2 square root gamma, right? So it's basically a slightly more contrived version of what Rishi was talking about in the previous talk. Right? Got a few more extra orthogonality assumptions just to make our life easier. And so the model we're going to consider is a single layer Rayleigh network trained with GD and hinge loss. So this is the following form. We're only training the inner layers and we're using Rayleigh. The output layer weights of the Rayleigh network are going to be either -1 or +1. We're going to assume balanced numbers of -1 and +1. Again, just the ease. And so we can visualize that as follows. We've got our input. It comes in. It's hit by, we have some coefficients here on these green lines. These are the things we're training. Hits by Rayleigh. And then we have fixed output weights here. Okay? So we have 2 types of neurons, positive neurons and negative neurons. So then we are using the hinge loss. So just to remind you what the hinge loss looks like. So I think you probably would have seen this in Kedal's recitation period. It's basically the max of 0 and 1 minus yi times by the output of the function. Okay? So what this does is while the product of yi in our prediction is basically what this thing to be, they're going to be the same sign, but then once that quantity gets above 1, we just say we're not interested, we fitted you, we'll go and try and fit some other ones now. Okay? And then we're going to run gradient descent on this problem, and so we get the following form, and this is what's quite nice about working with the hinge loss in this setting. You'll see that essentially our weights, their updates, are essentially just a linear combination of each label multiplied by its feature. Okay? So this looks very much like a linear problem. We're just doing, instead of being, as it were, in a linear one. The thing that makes it confusing or a little bit harder is that we only include samples in our update which satisfy certain properties. So firstly, they need to be active. So firstly, the input needs to activate the neuron in question. So the inner product of the neuron with the input needs to be greater than 0. And secondly, it can't be fitted yet. So we need the loss not to be 0, the hinge loss on that point not to be 0. So this kind of allows us to really consider a kind of combinatorial problem where we're counting the number of bad versus good updates, like corrupt or clean updates, over some interval of time, okay, of the optimization procedure. Okay, so let's talk about some results maybe. So I'm going to summarize the kind of findings, and then we'll go through a kind of, I guess, a picture, but a proof by picture to try and give you some intuition to how you might go about doing that. And so the main takeaway really is that we get these 3 distinct training outcomes, benign, harmful, and no overfitting, as we vary this gamma parameter between 0 and 1. Okay? So the strength of the signal increases and decreases, we see our model will actually fit or behave in quite different ways. So first of all, we have the no overfitting, or signal dominant regime. So when gamma is sufficiently large relative to n and d, so we're thinking gamma, roughly speaking, bigger than n to the minus 1, then our clean training data point is going to have 0 hinge loss. Our corrupt training points are all going to have loss 1, so they've not been fitted. And then the network will also asymptotically have optimal generalization error. Okay? So in this setting, we're basically just not overfitting, we're ignoring the corrupt points and just fitting the clean. We then see gamma is a little bit smaller than that, but not too small. So really, this quantity may be a bit confusing, but I would roughly think of this as gamma equal to 1 over n. Gamma roughly 1 over n. Then we see the following. We get this kind of interesting, quite sensitive, benign overfitting regime. And here we have that when we have the clean training points of 0 loss still, so we fit these points perfectly. We also fit the corrupt training points, so we interpolate the entire training set. But then also the network still has asymptotically optimal generalization error. So it's a bit similar to this one, but here where we didn't actually fit the corrupt training points, we still managed to fit the corrupt training points, but it doesn't impact our generalization error. Okay? Here we've kind of proved, in some sense, that or we will prove, or I'll show you how we can prove that we actually see this. Then we also have the harmful overfitting or noise dominant regime. And so this occurs when gamma is pretty small, right? So gamma is our signal strength, just to remind you. And here we'll see again that the clean training points have 0 loss, but the corrupt training points have lost 1, and the network has generalization error bounded from below. Right? So it doesn't matter how big n is, we're always going to see something. We're never going to get that nice asymptotic optimization, generalization error. Yes?
So for the no overfitting, you require the corrupt training points to have lost exactly 1 or just omega of 1?
They do have to have loss exactly 1, and the reason for that is that with ReLU, they get zeroed they lie in the kind of dead half space of every one of the neurons. So what happens is over time, what basically happens is that the neuron, the whole entire network ceases to activate on any of these corrupt training points. And because of that, once it ceases to activate, then it won't update further, and so we've reached some kind of stable condition. Hopefully I can give some intuition to that. But yeah, good question.
So here D is always larger than N?
D is going to be big. I'm going to show you our assumptions. So we're going to need D like n squared log n for these results, which is huge. So we're going to basically be relying on the near orthogonality of each of these noise components. Because if they're not too orthogonal, then if we have 2 quite correlated noise terms, then the activation of one input on a neuron and another doesn't just depend on whether they share the same signal component, it also depends on whether they share the same noise component. And that makes understanding dynamics like horrendously hard. So this is a big problem with lots of the analyses on benign overfitting at the moment. D in each case has to be n squared log n. So the n squared log n, where does that come from? So if you want to use some kind of concentration bound on the inner product between 2 random uniform vectors, then you basically need n to be like log n for this thing to decay quickly. But then there's n points in our training sample, and that means there's O(n) squared pairs. So when we multiply that all together, we have D needing to be n squared log n. But yeah, it was a good question. So this is the thing we're going to focus on. I'm not going to discuss all of these because I don't think I have time. How am I doing for time, by the way?
Good. You have like 25 minutes.
25 minutes, perfect. Alright, and so then maybe just to convince you that I'm not just spouting things, and we do actually see some practice, if you run experiments with the data model I've described, then we'll see the following. So we have on the left-hand side a heat map of the corrupt loss. So you might not be able to read, but this says log 2 gamma. So up here is a log scale of the gamma term that we're looking at. And this is negative, of course, because gamma is always between 0 and 1. On the bottom, we're increasing n from left to right, okay? So making our training sample larger versus smaller. So, because remember, all of our gamma inequalities, we need to see these 3 different regimes. It's kind of gamma relative to n and d most of the time, but d is also essentially a function of n, so we're mostly thinking about gamma versus n. So that's why all of these plots are log gamma versus n. And then the middle one, so for the corrupt loss, it's not coming up super well, but there's actually, you can see here, a very sharp phase transition between fitting the corrupt loss and not fitting the corrupt, totally fitting the corrupt loss, and not fitting the corrupt loss. Okay? So in here, if you just kind of bounce over this line, here we're fitting our corrupted data, whereas in this regime over here, we are not fitting our corrupted data. Okay? So these correspond to the no overfitting and benign overfitting, and eventually overfitting regimes. Okay? In gamma, the kind of benign overfitting regime is kind of following almost just off this phase transition. Then the clean loss pretty much always is just going to be fitted regardless of what gamma is. And then if we look at our test loss, we see that we said, well, we are kind of predicting that gamma has got to be roughly 1 over n. So if we take log gamma, we're expecting to see minus log n. And so hopefully you can kind of see the difference like a negative logarithm right here, this phase transition here, between having 0 test loss over here, so generalizing very, very well, and generalizing quite poorly on the other side. Okay? So here we have, this would be our harmful overfitting regime, this would be our no overfitting regime probably, and along this line here we're getting a kind of benign overfitting regime.
Could you please explain what the difference is between corrupt loss and test loss, big loss?
So sorry, corrupt loss, this is our training data. So remember we've got these corrupt points in our training sample. These are the noisy ones that have their label flipped. And so these points we show that are fitted, like, it depends on the regime we're in, but we're seeing very different behavior. Our clean points are basically always fitted, but depending on the relationship between gamma and n, the corrupt points may or may not be fitted. And I'm trying to show there's a sharp phase transition here between the two. Does that make sense?
So this is a data set where you have given the problem data, but now you have flipped some of the labels,
Yes.
and we're just plotting the error on training that data.
Yes.
What about the test loss?
Test loss is a new, this is basically sampling new points, but without the corruptions.
All clean in test?
Well, sorry?
All clean.
Yeah, the test we're assuming just for simplicity is all clean. Otherwise we just have to move everything up by noise level according to like the data is. So no, the questions. So yeah, are these figures kind of clear? Any other questions on them? You do? Yeah?
Why do you get an ability to, like, why is there a reason that looks like you can fail to correctly fit in clean data with various high gain?
Down here?
Yeah.
Oh, very well spotted. Okay, so this is because D's fixed. So when D's fixed and N grows, if we're just randomly sampling vectors, we're going to start to like contradict the near-orthogonality condition that we need. So this is basically an artifact of the fact that our D is not growing. If it then gets really, really large and D is smaller than N, say, or considerably smaller than N, then clearly they're not going to be orthogonal, and then all our theory kind of goes out the window. Good question. I was hoping no one would spot this. You spotted it.
No, but this is the result of training, right?
Yes.
Yeah, but why wouldn't you be able to reach zero loss?
So sorry, why didn't you
Why
do that?
would you not be able to reach zero loss on clean data that is inaccessible?
Well, I'm not saying you, it's not that we're not doing terribly, right? But it may be I need to keep training for a bit longer. I'm only training for, I think, 5,000 iterations in GD. So if I kept training, I possibly could, like, fit this well. But yeah, it's just, I guess the time to that is slower. But yeah, that's a good question, yeah. All right, so hopefully some experiments that show the theory is kind of correct. Oh, so okay, no, hang on. There's one section we have to say that no, I'll talk about that later. All right, so let's look at a proof sketch for this. All right, so first of all, let's highlight the assumptions we need. So I've got some delta, which is some failure probability between 0 and 1/2. I've got this rho parameter, which is a bound on the magnitude of the unit products of the noise. And then this lambda w is a bound on the norm of weight initializations. I'm going to assume my network is a really, really small weight initialization. And then k is the number of corruptions of each sign in our training sample. So I'm saying this is some small proportion, small fixed proportion of the training data. And then once again here, I'm saying D here is C rho to the -2, but you can think of this as we were saying earlier as like n to the n squared. So rho is like roughly speaking like 1 most of the time. And then lambda w we're saying is a small fraction of the step size of the output. Okay, so these are the three assumptions we need. And then the question is, okay, so visually, how could our network finally ever fit? So what we want really is that the positive inputs, and we give it a positive input, because remember at test time, we're assuming there's no noise, we want plus points to basically just activate positive neurons. Okay? I'm just adding up a bunch of positive things, the output here is going to be greater than 0. Yeah. It's a very simple way of getting what we want. It's not sufficient, so it's not necessary, but it is sufficient. Right? And the same thing on the right-hand side. If I input a negative point, then I want it to strongly activate negative neurons. And then when I add all these things up, it's going to be less than 0. So this is a very simple and sufficient, but not necessarily set of conditions. So I really want kind of very particular activation patterns that are going to give me the kind of the correct outputs at test time. We also want, on training. So sorry, yeah, the prior example was on points in my training sample. Then when it comes to generalization, so putting a new test point in after I train my network, what I want is the activations on, say, plus V, so the signal component. I want this to really strongly activate positive neurons, and the negative V to really strongly activate negative neurons. So I want my negative neurons to learn a minus V component, my positive neurons to learn a positive V component. And why this is sufficient to give us good generalization is that because we've got V really, really big, the noise component of our test point is going to be roughly orthogonal to all the noise components of those in the training sample, right? So in some sense, the common thing that all of our points have at test and train time is this V component. So that's going to be the thing that dictates how well our model generalizes. Okay, so basically I'm now going to try and show or sketch a kind of path to how you might expect to see these kind of activation patterns at the end of training, right? So this is going to kind of follow that. All right, so first of all, initialization, we have random activation patterns, right? So I've got some random Gaussian weights, for example, or uniform weights, doesn't really matter too much. I've got the very small magnitude, but my point is because of that small magnitude, one update is sufficient to ensure signal alignment. Okay. And so the reason why one update is sufficient to ensure this alignment is that most neurons, if we just think about it probabilistically, are going to be activated by approximately n clean and k, much less than n, corrupt points. So the clean and corrupt points, remember, have opposite B components. So they're pushing in the opposite directions, right? But if nearly every neuron is being activated by n clean and k corrupt, then this means we're going to be pushing them in one pretty solid direction, okay? Because the kind of corrupt points just kind of drowned out by the clean. So after one update, you essentially have this alignment of the signal with the output weight of the neuron in question. So if I'm looking at neuron J, and it's got an output weight minus 1J, then the correlation of that weight with V is going to match, right? So this means that after one update, my positive neurons, just to reiterate myself, sorry, are now, they now kind of activate strongly on plus V, and my negative neurons activate on negative V. Okay, so this is what this looks like then. So our clean points, our clean points are going to have this type of activation. Because it's just been one update, and eta's small, right, then the loss is still very small overall. We've got quite weak activations. But over time, these activations are going to grow. At the same time, our corrupt points have, because they have the opposite V, their label, the V component they have is opposite to their label, then they're going to have activation patterns that look a little bit more like this, right? So our corrupt positive point has a negative V component, so it's mostly activating negative neurons. But there's maybe just probabilistically, you can show the initialization, you're going to have a few of what we call carrier neurons, and these are going to carry these corrupt points through training. So, phase one, essentially we can break the analysis down into two phases. One in which the clean points are fitted, and the second one in which the corrupt points are fitted. The point I'm trying to say is that early on, clean points, the signal and noise components, for clean points, the clean input point is going to push a positive neuron in the same, or their noise and signal component is going to push the neuron in the same direction in some sense, their activation. But for corrupt points, it's going to be the opposite, right? So in some sense, the signal component, the activation of a point with that neuron, these are going to be pushing against each other, and in some sense cancelling out. The kind of purpose of this behavior. So most neurons are activated by approximately n clean and most k corrupt points. The change in activation from iteration t minus 1 to t is therefore going to look something like plus or minus eta, and then there's this beta I term, which is the minus 1 and plus 1, n gamma, plus 1 minus gamma. And so if we're thinking about gamma being roughly 1 over n, then this is going to be just 1. Gamma, if n's large, then we can think of 1 minus gamma as approximately 1, so we're just getting the following. And so this means clean points are roughly changing by plus or minus 2 eta at each iteration, whereas corrupt points are changing by approximately 0, and a very small amount. So what I'm basically trying to say here is that in this early phase of training, before we fitted any point at all, the clean points are actually getting fitted, right? Their activations are growing in strength. But the corrupt points are kind of really staying kind of close to where they were at initialization. Okay, so now if we kind of, I guess, play the tape forward, as our kind of number of iterations t grows, we see the clean points, the activation strength is growing, right? So that's what this, the intensity of the orange is meant to indicate like strength of activation, right? So the size of the inner product of that neuron with the input. On the other hand, for corrupt points, as t gets wound forward, we don't really see much change in the activation strength. So by the end of this first phase of training, and the first phase of training I think of basically up to the point the first clean point is fitted, right? So that she is the output of the network on that point is say like plus or minus 1 depending on whether the point is plus or minus 1. Then at this point, this is the first phase, we see these kinds of activation patterns, okay? But then in the second phase, we can kind of think of our clean points now as being roughly fitted or very close to fitted. And now, really, it's the kind of time or turn of the corrupt points to reach influence dynamics. Okay. So clean points infrequently contribute to updates now because they're mostly fitted, so they're not participating in the updates. And the change of their activation strength is now roughly 0. Corrupt points now, therefore, kind of dominate the dynamics, And we're saying that now each neuron is roughly activated by k, much more than n corrupt points. So now if we do the same kind of analysis we had before, the change in activation on corrupt points is going to be plus or minus eta versus 0 for the clean points. So in the second phase of training, we can see that our activation of corrupt points is growing at roughly plus or minus eta, while it's not really changing at all for the clean points. So again, winding the kind of tape forward now, we're in phase 2, so working from t equals 100. For these corrupt points, we see their activation strength on the neurons of the opposite label sign are going to grow weaker because they're decreasing by about minus eta each time, but they're getting stronger on these carrier neurons, right? These 1 or 2 neurons that were just lucky enough to activate at initialization. Okay? So over time, we get the following, right? Something like this. So at the end of training, our corrupt points are being fitted because they're activating essentially a small proportion of neurons of the same sign very strongly, based just on those neurons learning their noise component. That's the kind of high-level idea of how we can fit the noise. But at the same time, the kind of thing that's interesting is that we're not losing this signal component that we've learned, this plus or minus b. And so these are still activating the right sets of neurons correctly, and so we're still going to generalize well on new testing. Okay, so that's pretty much everything. Maybe, yeah, how much time have we got left?
Roughly 10 minutes.
Roughly 10 minutes, okay, alright. So I was that's pretty much my talk. I was going to maybe talk about a small exercise for people. So I admit it's probably quite hard to try and understand the main ideas, but if anyone's interested in trying to think of a very simple, okay, I'll give you this challenge maybe, or this problem, so maybe this will work. But imagine we're looking at the perceptron case that Kedar was discussing in recitation. Then we can think about, like, can the perceptron algorithm also overfit? Okay? And then maybe you can consider the following problem, right? So we're thinking about the perceptron algorithm, and I'm going to assume my data, once again, looks similar to the form I was describing up there. So maybe we have some gamma component of some signal, which maybe dictates the sign in some sense. And then we have a 1 minus gamma term for some noise term. Right, so once again, we're considering some kind of similar signal noise decomposition. And then, once again, I've got some of these are corrupt and some of these are not corrupt, but we can use then the ideas of the perceptron algorithm. Right? So we know that the perceptron algorithm terminates in some time, so t is going to be less than or equal to, I think in this case, if we make sure this is normalized, then it's just going to be the kind of W star squared, where W star is a linear classifier of our problem. And then the idea that we can show to try and show that we get benign overfitting is to basically use this T and show that the overfitting case would contradict would require a number of samples that's got to be bigger, or a number of updates that's bigger than our upper bound that we developed through the perceptron algorithm. I think this isn't really working because it's too small, so I'll probably just stop there. But if anyone's interested, I can try and describe what I'm talking about here. Okay, that's it.